Hello, my name is Tyler Erb, and today we're going to talk about mass points. Mass points is used in a lot of math competitions whenever we have ratios of side lengths. We don't actually need to know the actual side length, but we can use ratios and a point that will divide them up to figure out things like area or just ratios of other side lengths. We're also going to talk about cVians. You've seen cVians before. If you were to have a vertex, right, let's call this vertex A, and it goes to, say, some other point on its opposing side. So A to D would be a cVian coming from A. Mass points, I like to always say, is the world's worst teeter-totter, right? You can also kind of think of it as a set of scales. We're trying to balance out the ratios of the side lengths versus the actual mass at the end of each vertex. For example, let's say that AB to BC has a ratio of, I don't know, let's say 3 to 2. So if we have a ratio of 3 to 2 here, that means that we would need C to have a mass of 3 and A to have a mass of 2. This will help our entire segment AC balance itself out. We also know that if this is 2 at A and 3 at C, that the middle point B has to have a mass of 5. That point that divides your segment is always going to be the sum of the masses of the vertices. Let's look at another problem. In this example, we have a pseudo triangle here, right? We could draw this and make it a triangle, but we essentially are able to balance C with both AB and both PD. So we know that if we were to have, for example, this be a 3 to 2 ratio, let's flip that just so that way it kind of looks like semi-drawn to scale. And this is, let's say, 1 to 4 ratio. We'd be able to figure out C being the center of mass. Now, you might say, well, we can just do the same thing we did, right? Assign 2 as a mass of B and 3 as a mass of A, which would make P have a mass of 5. The problem here is that now we have this 4 going with the 5. And while we can deal with fractions there, we might not want to, right? So instead we go, well, if I take the least common multiple between these two, I could have it balanced and deal with integers the entire time. Let's take that back. Let's instead call this mass 20. The 4 from CD and the 5 from AB. That means we're going to multiply this whole ratio by 4, so this becomes 8, and this becomes 12. And here we multiply this by 5, right? The 1 becomes a 5, the 4 becomes a 20, and C would have this central mass of 25, right? It's still the sum of P and D here. We're going to use that principle of balancing out our triangles and using the least common multiple to try to make these problems where we can create ratios. Okay, so here's our first problem. We're told E splits segment DA into a 2 to 3 ratio. We don't actually know the length of DA, but we do know that the ratio of its sides is 2 to 3. We're also told AB to BC is a 3 to 5 ratio. So our first thing we want to do is balance our masses, right? We don't want to just start assigning, let's say A is a mass of 2 and B is a mass of 3, because that may not help us out, right? In fact, if we look at BC, that tells us that A should have a mass of 5. So we're going to use the least common multiple between 5 and 2, which gives us 10. Which means along all of segment AC, we're going to multiply it by 2. So if A is 10, then that means C has to be 6. This also tells us that on DA, we're multiplying by 5, right? That's times 5. So that means D is going to have a multiple or a mass of 15. From here, we can also find those central masses. We know that E has to be the sum of both A and D, so it has to have a mass of 25. And B has to have the sum of A and C, so that gives us 16. This tells us that F, which is kind of the center point of BD, right, has to have the sum of the mass of D and B, or a mass of 31. And we can check this out, right? Our triangle should be balanced. So either way we look at it, if we're looking at DB or EC, it needs to have a mass of 31. And so we check 25 plus 6. Yep, that still adds up to 31. Now, our goal is to figure out the ratio between DF and FB. So if this is DF right here, and B has a mass of 16, that means that DF would be 16. And that also tells us that with a mass of 15 at D, we would have FB be 15. Our goal is to figure out DF to FB, so our ratio would be 16/15. Let's try another problem out. We're trying to figure out CE to DE, and we're told that DF to BF is a 5-to-1 ratio, right? Essentially, it says it equals 5, which tells us we can use 5-to-1. So we can say this is 5 and BF is 1. And we're also told AF to EF is a 6-to-1 ratio. Again, I will say these are definitely not drawn to scale. Don't try to say, well, AF doesn't look like it's 6 times. I agree, right? My drawings are not to scale, and I apologize for that. But now we look at trying to balance our triangle here, right? If we're looking at trying to balance at point F, we realize that F should have 7 from segment AE, and it should have 6 from DB. So what we're going to do is we're going to get that least common multiple, which is going to be 42. Which means we're going to multiply everything along AE by 6. So this becomes a 36 at E and a 6 at A, right? 1 times 6, 6 times 6. We're going to do the same thing over here with DB, but we're going to have to multiply by 7. So that gives a mass of 35 at B and a mass of 7 at D. Finally, what we can do is we're able to figure out what C is. If we know D plus C has to add up to E, and we also know A plus C has to add up to B, either way we do it, we realize C has a mass of 29. Our goal is to figure out CE to DE, and so this 7 becomes the ratio of EC, and this 29 becomes the ratio of DE. And so our final answer is 7/29. Again, the big piece here is that we had to kind of create that central mass that's going to balance out the rest of our triangle first, and then go from there. I want to talk about one more principle that's going to be really helpful for us when dealing with mass points. A lot of times we'll talk about this as Sivas theorem, but really all we're doing here is looking at ratio of bases to heights. So we're going to use bracket ABD to talk about the area of ABD, right? This just means area of ABD, or this is the area of ACD. And we know essentially that these two triangles share the same base, and they both share a common vertex at A. So what this means is if we were to try to figure out the area of ABD, for example, we'd say it's 1/2 the height times the base. Well, the base here is length BD. And for ACD, it would be 1/2 the height times its base, which is DC. And because they share that same base length, their height is also going to be the exact same, right? And we could move A anywhere along this line parallel to BC, and we get that exact same height. So we're able to reduce here and simplify out our 1/2, reduce those to 1, and H over H will also reduce down to 1, and we're left with BD over CD. We can use that ratio of side lengths to help us figure out other areas if we were to say split this triangle even further, right? Maybe we draw a line here and now we're trying to figure out the area of this quadrilateral. There's a lot of things we could do with it. So let's see how we could apply this. So in this diagram, we have EBF, BFC, and DFC as the given areas, right? We know BEF is 12, the area of BFC is 18, and the area of DFC is 9. Our goal is to try to figure out how we can use these areas to help us figure out what quadrilateral EADF is, right? So our first thing we're going to realize is we can split this up into big triangle EBC. And we know that the ratio of their bases is 12 to 18. So that means that the ratio of their sides also has to be the same, right? Because they share that same base, EC. So if this is 12 to 18, we can simplify this down to 2/3. So we know the ratio from EF to FC is a 2-to-3 ratio. We could do the same thing here with triangle BDC. We know it's split into triangle BFC and FDC, so that means we should be able to find a ratio of their bases because the height has to be the exact same. Well, if BFC has an area of 18 and FDC has an area of 9, we can split this up into a 2-to-1 ratio. And now we kind of go back to our similar problem, right? We say, well, F has a shared kind of point here at F, and F must be balanced on BD and on EC. So here we would get a mass of 5 along EC, and we get a mass of 3 along BD. And so what that means is we can take the least common multiple of those and make it have a mass of 15. Once we know it has a mass of 15, that means we're going to multiply our ratios on EC by 3, which makes this a 6 and this a 9. And we're going to multiply along BD and get by 5 to get this to be 10, and this will be 5. Either way we try to find point A, we're going to get a mass of 4, which is great because that means our triangle is balanced. Now what we're going to do is we're going to look at a ratio of our areas, right? We know that if we split up the entire triangle into, let's say, these two pieces, we're going to split it along EC. We know that the area of EAC over the area of BEC should just be a ratio of their areas and their base lengths. If we're talking about their base lengths, this should be a 5-to-4 ratio. If we're talking about their areas, the top area is x plus 9, the bottom area is 12 plus 18. So we can set this up to 5/4 equals x plus 9/30, and then from there we're just able to cross multiply and solve. This gives us 4x plus 36 is equal to 150, which tells us that 4x is equal to 114. And then we divide by 4 on both sides to get x is equal to 28.5. And that's our final answer. I hope you enjoyed this first video of mass points. I think it's really useful anytime we're given a ratio, or if we're given areas with shared base lengths, right? That's going to help us be able to divide up our triangle or our figure and do a lot of fun things with it. Thanks for watching.